Good morning, Alvin.
Good morning, Dr. Terrell.
You realize you're now the representative for Chem 55.
How are you?
I'm good. I'm good. I'm good. Just making observations.
I have a question about the practice test.
The one that we took.
The one that was just to like test the browser.
Yeah.
Well, will you be like changing the grades? Because like I just didn't pick the first choice.
Oh, the fake midterm thing? Hold on.
Yeah.
No. Don't worry about that. That's not going to count.
Okay.
I'm sorry. I made that with points for some stupid reason, but don't worry. I'll take those points out. I promise.
Okay.
Oh my gosh. Okay, so hold on. I gotta share my screen, right? That's what I gotta do here. So share screen. Number 2. There we go. Okay. Alrighty. I think I'm going okay here. So, my goodness, there's a lot of y'all. And it's all kinds of majors and everything. Like, are there any bio majors out there? Maybe. Should probably know this stuff, huh? Okay. All right. I'm going to get on with it. I promise. So, wait. Elvin changed his name back to Elvin? Elvin from Elvin? How odd. I kind of like Elvin better. I have to admit it. Okay. So welcome back to the land of data. This is the land where we're taking real measurements and making real conclusions, or, something has to give always. So we're always, the thing that gives here is confidence, right? So we're going to say, no, the answer is between this and this, right? 95% of the time, or 99, or whatever we want to say, right? Let's see, who is this?
And I'm gonna mute my teacher. Don't worry. Where is it?
Ana Lilia? Okay. Here I am. Yeah, you guys can see me, right? My little weird mug here up on the corner.
Yeah.
Yep.
Okie dokie. Excellent. Thank you. Okay. So, so what we're going to do is we're going to try to distill everything down to a universal statistic, and we're not going to use the z value from the Gaussian distribution. We're going to use the t value, because the Z value really only applies to very large data sets that are like Gaussian, you know, for sure Gaussian, and we know the standard deviation very clearly, right? So what we're going to do this time is we're going to use the similar but slightly broader distribution called the T distribution. And funny side note, the T distribution was invented by a guy named Gossett, who worked for the Guinness Brewery. And it sounds like a really kind of an interesting backstory to it, because Gossett and his buddies, they just sort of worked it out. Like, okay, so we have to they were kind of doing quality control at Guinness. It was like in the late 1800s or something. They're like, okay, well, how do we compare these values and be sure about it, And they weren't really statisticians or anything, I don't think, because they got corrected later on by someone more mathematically oriented and said, oh, no, you're supposed to be using degrees of freedom here, not just like, oh, thanks a lot, So anyhow, Gossett published all of his T distribution data under the pseudonym of Student. So and so there was no connection to Guinness or anything at the time. But I suppose, I don't know why maybe they made him do that. Maybe he just chose to. But in any case, so we're going to calculate a T value for every distribution in it. We're going to say, like, does T agree or not with the
No, I want it to be moist.
No. With the idea that there's no difference, right? That's called the null hypothesis. So, so the null hypothesis is that any difference that you're seeing is just due to random fluctuations in the data, right? It's just sort of an accident, just ignore it, right? And in order to get a statistic that reflects that, you calculate the T value. And, what we were doing last time was we're using T from a table, right? We were to calculate the confidence interval. And what we're going to do this time is we're going to calculate an experimental T value, and we're going to call that T calculated. And T calculated will come from the data. And what we're doing in this class is we're simply comparing that number to a number in a table, to a corresponding value in a table, and saying, is the calculated T value larger than the tabulated T value? So is the calculated larger than the tabulated? And if it is, then we reject the null hypothesis, We say, no, there really is a difference. We must reject this null hypothesis, right? And what that means is that given everything we know, there's a less than a 5% chance that the two data sets came from populations that have the same mean value, right? Like that if we just took more data, everything would clear up and the mean values would begin to agree better and better, And in this case, the difference is considered significant, This is the statistical significance, Maybe we can even say here, statistically significant, So within this world, there's basically 4 cases, right? 1, 2A, 2B, and 3. And in case 1, what we're doing is we're taking an average we measure it several times. We obtain the average and the standard deviation, and we're comparing it to some accepted answer, right? Like, is there a reason? Really, there's basically two cases here. It's like 1A, 1B, 2A, 2B, right? But we're saying, does this X bar agree with some accepted or expected value mu? So like, for example, in Chem 155, we measure vitamin tablet. We say, okay, we get so many milligrams of iron, zinc, and everything else in here. And we ask ourselves, does this answer agree with the label or not, right? And that means it could be lower or higher, right? But is this, it's actually the same thing as saying, is the answer within our confidence limits, And so it's kind of almost the same thing as asking that, right? And so, and that you can ask that question. You can also ask sort of a one-sided version of this question, which is, is our answer above the critical limit or below? Well, let's take the above case first. So first we're asking just, is the answer within limits? And second, we're asking, is it above that limit? So like, if you're measuring something toxic in groundwater or something, you don't care if it's zero. You just want to know if it's above a certain limit. And that's called a one-tailed test. The normal test is a two-tailed. So there's like, we can say 1A, two tails, 1B is going to be one tail. Right? And these are illustrated later, right? And then case 2 is where we're comparing two averages, right? We've got two data sets, right? There's no answer mu from down on high, right? This is not like defined. But we have two data sets, both experimental. You got X bar 1 and S1 and X bar 2 and S2, right? You're saying, well, do these methods agree, right? Or is the difference just random, right? Because there's always going to be a difference. And so you're just going to ask yourself, is this difference significant? And in this case, we'll calculate a T, and we'll compare it to the two-tailed critical T values or tabulated T values, right? And then the last one is less common. I don't really think we're gonna practice it very much or anything, but it's out there, so you should know what it is. So it's called the paired test, and that's where you make a bunch of different measurements, but you measure them each with two different instruments, or two different methods, or from two different labs or something like that. And you have like the same sample measured in way A and measured B and way B, and then the next sample measured A and B, then the next sample measured by method A and method B, right? And you have all these pairs of data. There's all these differences, and you can say, well, if the differences are really large, then that means that the methods are different, right? So that's like case 3, right? Okay, so on with the show here. So let's try a case 1. right? The coal sample is certified, right? This means that it's a certified reference material, right? Or a standard reference material. It's an SRM, right? Oops. Okay. It's an SRM, and it contains 3.19% sulfur, right? It's a standard reference material, and so we believe this value, right? Then you apply a new analytical method, and it gives you a little more. It gives you these 4 answers, and you're saying, wow, is this difference really significant? Is this mean value of 3.26 plus minus 0.041, is that really different from 3.19? And so what you can do, you can calculate the confidence interval, right? And x bar plus minus t s over root n. So this is the tabulated t value, right here. 3.18 is for 3 degrees of freedom and 95%. Those are the only 2 ingredients that go into this number: the degrees of freedom and 95% confidence, right? T, that value times s over root n. You make this confidence interval around x bar, right? You get this, and say, well, this value, 3.19, lies outside of the interval defined by this measurement here. Yeah? And so this measurement gives a different result from the known, right? So another way to do this, okay, hold on. Okay, so this is basically, so you can also flip this around and calculate the t value. And so t will be x bar plus minus s over root n, I'm sorry, n over root n over s, right? What? Oh, forget it. I forget. I'll get to that in a minute. Sorry. But I'm trying to flip that around in my mind. It's not working. I'm not having a math morning. So let's see here. So if we want to compare replicate measurements here, we can compare replicate measurements when the standard deviations are not significantly different. So this is 2A, right? And what we're going to do is now there's no mean value. There's no true mean here, right? We're just talking about comparing bicarbonated horse blood, and in this case, the calculated F value from the ratio of the standard deviations is less than the tabulated F value. So these measurements are not significantly different. So this is an important point, that this gives you permission to use this formalism here, this guy and this guy, right? The t value, x bar 1 minus x bar 2 over s pooled times n1, n2 over root. So this is x bar root n over s, right? That's what I meant to say. So the difference between x bars times root n over s, right? So this is a weighted, this is a reduced n value, and s pooled is sort of a weird way of aggregating s, right? So you can take I prefer this bottom formulation here because you almost always know S1 and S2. S1 squared times N1 minus 1 plus S2 squared times N2 minus 1 all over N1 plus N2 minus 2. Right? The degrees of freedom for this guy is N1 is 10 plus N2 is 4. N1 plus N2 is 14 minus 2 is 12. So, okay. Hold on. Let's see. So, hold on here. Oh, yeah. So, this is the same one, right? So, S pooled here is 0.33. And the T value that comes out, this 0.33 comes down here, right? Is 0.30, right? So you say, well, is this T value significant given all the other things that we have? So the T value is way less than the T table, right? 0.3 is way less than 2.13. So we say that there's a less than 5% chance. This less than is connected to this less than here. That the two data sets came from populations with the same population mean. And this is not a significant difference, right? So this means that any difference that you find in these, based on what we have, 10 measurements with one instrument, 4 measurements with a new instrument, these standard deviation, any difference that we find between them cannot be distinguished from random chance based on these measurements. If we refine it, then maybe we'll find a real difference. But based on 36.14 and 36.20, based on these small differences, there's nothing significant about the differences, right?
I have a question.
That's right.
Did you said that in our case, because T-calc was less than T-table, then there is a less than 5% chance that the two data sets came from the same? Or
Yes.
but that's like a bullet point under if T-calc is greater than T-table. So that's when you're rejecting the null hypothesis. So wouldn't it be like the other
Oh,
way?
okay. So I correct me if I'm wrong here, but to reject the null, right? That means no, they're not the same, right? Null is the same,
Yeah.
and reject is no, they're not the same, right? And if I misspoke, then I'm super sorry, but let me try and get it right here. The T-calc is less than the T-table. Therefore, there's less than a 5% chance that they're the same, right? Holy shit, I'm so confused now. Wait a minute.
Isn't it like there's
Wait a minute.
isn't it like because it's the T-calc is less than the T-table, then there's like a 95% chance that they are from the same?
Well,
So now we cannot reject the null hypothesis.
You can't say that. You have to say it all in these negatives. Right? I'm sorry. Alvin, what were you saying?
Oh no, I was just saying since it's not greater than like table value, calculated is not greater than table value. So here we cannot reject the null hypothesis. So,
Right, we can't reject, right?
yeah.
So we accept the null hypothesis, T-cal is less, right? So if it's greater, then we reject. But if it's less, then we accept. You know what? So this here, there's less. So this whole piece of shit right here, this and this, are in conflict with this, right?
Yeah, that's why I was kind
So
of confused.
let's fix this goddamn thing. I'm sorry, I didn't catch that earlier. So let's say if t calculated is less than t table, then we accept the null hypothesis, right? Then there's so how do we say this? There's less than a 5% chance that they're from the same population mean. Means that there's only less than 5% that they're the same.
Yeah, because when I like think of that like statistically, then it like doesn't make sense because it's like why would you accept it if it's such like a little percentage, you know?
Well, but you're accepting a null hypothesis, right? You're accepting that there's no difference, right?
Yeah, but I'm just like looking at the bullet point. I was confused.
Right. Yeah, thank you. I'm sorry. Yeah. Okay. There is less than 5% chance that the two data sets. So this is for the greater than case. So if it's less than, then there's greater than. I think that's what we're supposed to do here. There's more than 5% chance that the two data sets come from populations with the same mean, right? I think that's the proper way to fix this. I think that's proper. I think that's proper. Yes. Okay. So basically, in
And
this,
also, Dr. Terrell, can you go
yes.
2 slides back? Just 2 slides back. Or the
Yes.
one where we had the null hypothesis, maybe it's a little bit more back. Because there you had reject the hypothesis and the same 2 bullet points.
Okay, so
saying
this
less than 5% or something. So you can check that one too.
what? This one?
No,
Which one?
the one that you have the t calculated greater than t value.
This one? Or this one?
Yeah,
Not this
one. This
Okay.
one is. Oh, we just made this one actually.
Yeah.
I thought there was another one you were going through, and then you had the same 2 bullet
It
points.
must be.
Before.
It must be this one here, right? So in this case, yeah, this is the only other one we've looked at, right? And this doesn't actually calculate t. It uses the tabulated t, right?
Okay, never mind then. Cool.
You know, yeah.
Thank you.
I'm sorry, it gets a little bit confusing, and it's gelling in my mind as we speak too. You know, and I've only been fucking doing this for 20 years. You know, sorry. It's like it gets confusing sometimes. You know, so what it boils down to here, though, is that there's really two possibilities. The calculated t is going to be less than or greater than the t table, right? And I'll just put it in as plain as speak as I can. If t calculated is less than t table, there's no difference. If t calculated is greater than t table, there's a difference, right? Because t is proportional to the difference, right? If there's a large difference here, greater than the table, you accept it. If there's a small difference in here, less than the table, you You say there's no difference. Did I screw that up? I hope not. My memory's not good enough.
Professor,
Yes.
Professor, could you just repeat that one more time? I'm trying to solidify the
Excellent.
lesson
Excellent.
in full.
Excellent. I will repeat. I will.
Thank you.
So let's see here. So T is proportional to the difference between the two values, right? So if the T value is greater than T table, then it's real. If the T value is less than the T table, it's not real. That's sort of our cutoff, right? So in this case, the T value is less, the calculated T value is only 0.3, and that's way less than the tabulated value. So I just got confused because the wording on this answer was really weird, you know? And so in this case, it's less than, so we have to accept the null hypothesis. The null hypothesis, there's no difference. No difference here, nothing to see. T calculated is less than T table. Move on. That type of thing. Okay. So does that make sense, more or less? I'll let you guys mess with this in the calculations a little bit, and hopefully it will become clearer. Hopefully my stumbling about here has helped somehow.
Yeah,
Just so
for
you
me,
know.
for me, I'm just gonna think more about whether to reject or accept the null hypothesis, and not think about like the number too much, like behind it, unless like I don't know, maybe it like comes up as a question.
Okay, well, so let's exaggerate the differences, right? This is really helpful. Let me go to the pen, the dreaded pen. The dreaded pen, yeah. So let's say that we have method 1 gives us 25.6 plus or minus 0.1, and method 2 gives us NES is n equals 3, and 25.7 plus or minus 0.05, n equals 7, right? Oh wait, no, let's say plus or minus 0.25, let's say, right? Now, in your opinion, Ryan, are these values statistically different?
Do you want me to just calculate it real quick?
No, just give me your opinion.
0.25 and 1.
Yeah, no math. Just give me your opinion.
No?
These are not different. Exactly, right. And so if we calculated the T value, it would be way less than the T table.
Yeah, because it's only like a 0.15 difference.
Right, because the difference is 0.1, right? And the standard deviation here is 0.1. Standard deviation here is 0.25.
Oh yeah, sorry, I was talking about the standard deviation, but yeah, the means are like barely different.
Yeah, they're fairly close. The means are close. So the means are close. Therefore, there's no difference. Right? And all the math is just going to codify that. is just going to confirm that, right? I guarantee you the T value here is going to be like 0.2 or 0.1, right? Right? The T table, you know, for n equals 7 plus 3 is 10 minus 2 is 8, right? Will be, you know, we can look it up here. Hold on, y'all. Rank. We can look at the tabulated T table here. Oops, come on here, come on. No. T table, n equals, this is 8, 95 is 2.31, right? Is 2.31. You know, and so this calculated value is way less than 2.31. So there's no difference. You know, this is proportional to the difference. Oops, sorry. Damn it. So the T calculated value is way smaller than 2.31. 0.1 is proportional to the difference, right? And unless it's 2.31 or greater, then we can't discern a difference. So we say there's no difference there. Okay. That means I beat the dead horse. Does that make sense? Maybe?
Yeah, it does.
Okay, thank you. Thank you for releasing me. Hold on. I promise it will all become clear. So, all right. So let's do an example, right? So this has another twist, which is that the standard deviations are different. And this is a famous example. Who the hell was Lord Rayleigh? He's got a dweeby name, but he I don't know. He was a good scientist, you know, and so they made him a lord. Man, why don't they do that anymore? Anyway, but so I want to be a lord. Anyway, shut up, Roger. So so basically, Rayleigh did some experiments and he discovered oxygen. So, I'm sorry, he discovered argon. He discovered argon, right? And so the way he did it was by removing oxygen from air, you know? And the rest was all nitrogen, you know? And then, so then he measured nitrogen from air, and he measured nitrogen that he generated in the lab using a chemical decomposition, right? And then the mass of those two nitrogens was slightly different, you know? And so it's like, how did this happen? You know, that's kind of strange, huh? And so the difference with the chemically derived nitrogen was slightly lighter than the nitrogen from air, than the supposed nitrogen from air. And the reason is that the nitrogen from air has a heavier component in it, which is argon. You know, argon is it's heavier than nitrogen. Nitrogen's like 28, argon's heavier, right? So let's see, how much is argon? Periodic table. Argon is 40. Nitrogen is 28. Yeah, so it's significantly heavier, right? So, and it's only, and argon's only like less than 1%, right? But so you had to do this at high precision. So he weighed the nitrogen after removing oxygen, and he made the same amount of nitrogen from chemical decomposition. And then he compared the weights of these two guys. And sure enough, there's a statistical difference, right? You can tell that the difference is significant just by inspecting the data, right? Here's from the chemical data, right? It's a little bit more scattered. We've got, values around here in this range, 2.295, 6, 7, 8, 9, 3. So 2.298, 2.3, 2.32, right? And there's, how many of these guys are? 1, 2, 3, 4, 5, 6, 7. There's 7 of these guys, right? So these guys are these data right here. Oops. Are these data on the right. And this closely spaced grouping is from these data on the left. There's just 6 of these. These are all 2.31 or 2.309. Right? So you can tell just by looking that that if you make the nitrogen in the lab, it's going to be lighter than the supposed nitrogen you get from air, right? Because the nitrogen from air has argon. So the first thing, if you want to make a statistical comparison of these, is to do the F test on the standard deviation, right? 10143, 10137. Jeez, this is pretty damn close to me. So, so apparently these standard deviations are significantly different, right? Well, I'm not really sure that that's true, but let's go with it here. Basically, what you do is you can calculate the t value using x1, x bar 1, x bar 2, s1, n1, s2, and n2, right? These are the 1, 2, 3, 4, 5, 6. These are the 6 data points that you need to calculate the t value of those two populations, x bar 1, s1, n1, x bar 2, s2, and n2, right? Then in order to get the degrees of freedom with this, right, you would think, oh, it's just n1 plus n2 minus 2, right? But because the standard deviations are a little bit different, you got to use this complicated ass formula to arrive at basically the same conclusion, right? And so here, let's go through this. So this is basically just what I was saying. And then the T calculated here is, the degrees of freedom is 7.17, right? Which is 7 plus 8 minus 2 is actually, that's pretty, lot smaller actually. It's a lot smaller. It's closer to the lower degree of freedom value, right? So basically the T calculated is 21, right? And if we look at the tabulated T value, it's 2.3, right? So this is the tabulated value. And this is the calculated value, right? So this is T table. And T calculated is 21.7, right? So it's a short story, right? That since the tabulated value is so much less than the calculated value, then we have to reject the null hypothesis, right? Say no, they're not the same. And when I say that, I basically just look at the data. If it were a real close case, then I'd have to look at the definitions there. But if tcal is greater than t-table, we reject. If tcal is less than t-table, we accept the null hypothesis. Null hypothesis meaning there's no difference. Does that make sense to everybody? All right. So, all right. So let's do this next exercise here, right? And it's kind of a clever one because I looked at it. Oh shit! How am I going to do this calculation, right? And it says if the difference between two mean values were half as great as Rayleigh found, the standard deviations were unchanged, would the difference still be significant, right? So let's look back at the data here, right? The T calculated, we're saying that this same standard deviation, same degrees of freedom, right? Just half the difference here, right? So the degrees of freedom, this guy here, this 7 value, this would not change, right? Because standard deviation and standard deviation 2 and 2, these are all the same. And then that would be equal 7.17. And then T calculated here is equal to x bar 1 minus x bar 2 over x bar blah, blah, blah. All this is just going to be half of what it was, right? So instead of 21.7, T calculated will be equal to about, that's going to be about 10 point, what is half of 17, or like 10.8, right? Right? So, and then instead of 21.7, right? So now, if T calculated was then it's still significant, right? Because the table is only 2.365, right? Does that make sense? Anyway. Okay. I'm going to assume that the silence means I'm going too slowly or something. And if not, just let me know. And then here is, next slide. So, and here's paired values, right? Paired values is just where you have two different ways of measuring the same thing. You've got one sample that's measured with the two different methods, the second sample is measured, the third sample is measured, And you just take the difference from all these, take the average of the difference, standard deviation of the differences, number of differences, T calculate, and T table, right? And you can, then you can compare these values, and that's all you need to do. And honestly, we're not going to do this in this course. So it's just so kind of have some awareness of this. That's all we need to know. And just see how. And then, and then lastly, but not leastly, right? The thing that I understand the worst is the question of, does something agree or is something only above, only below? But let's say it's only above a regulatory limit, right? So in the case where what we've been doing here is asking if values agree statistically, right? Now, if we have to ask a different question, which is our value above a regulatory limit? Regulatory limit here. Regulatory limit. This is the key word, right? Then what we do is we take the same area, but we compare it just to one side of the t-distribution. Doesn't matter which side, it's just whatever one side, right? Take 5% of the total area there, and that will give us a slightly different t-value. And this is called a one-tailed test, right? And you can just use a one-tailed test. Blah, blah, blah. So I'll let you guys work through this nonsense, and then we'll do Grubbs tests, and we'll move on to chapter 5 mañana. Or I'm sorry, on Thursday, rather. We doing okay so far? Did everybody get that I updated the homework and yeah?
Yep.
Yeah.
Excellent. Excellent. I've got 2 frequent responders. Taryn is responding. Yay! Alrighty, guys. Thank you so much. And I look forward very much to sort of seeing your names on a screen and interacting with Alvin, Ryan, and Michaela, and a couple of other folks. Maybe Taryn on Thursday. Okie dokie, guys. Bye-bye.
Hi, Dr. Terrell. Thank you. Have a good one.
Thank you,
Alrighty.
Professor.
Alrighty. Thank you, guys. Bye-bye.